Now, this is, I think, one aspect which we can spend some more time now. And the idea is to make use of like just convolutional network. We don't want fully connected layers. All right, let's see how this can be done. And again, there can be a lot of different use cases why we need this. So what we'll try to do is like first we'll try to understand how this can be done, and then we'll try to understand like how this is actually different from neural networks when we have neural networks at the end. And we'll try to understand if there is any difference in terms of number of parameters which are required in this case and in case of when you have like a neural network at the end. Okay, so let's talk about the positives here. So you know that if it's a convolutional network, you don't have to perform any flattening or something. Okay, so you will never do like you have your spatial structure, you will never lose that correspondence. You don't need any fully connected layers, which you know like requires a lot of parameters, which means that you will be always able to share the kernels, okay, because you're not flattening. And then whatever kernels you have, you will use the same kernel across your spatial extent of the image or of the activation maps. So let's try to understand how this can be done. And it's a very simple trick actually. And later on you will be thinking, do we really need this? And again, it's debatable. And of course, there are like a lot of different use cases. So the trick is, what you do, you just reduce your spatial dimension to 1x1. Okay? For example, let's say your input image is 28x28. So far, whatever models you have designed, like for your programming assignments or whatever we have discussed in the lectures, you start with some image, then you have convolution layer, you have max pooling, you try to reduce them, but eventually you end up with like, let's say 7x7 and some channels, right? And then you directly flatten from there. Now the trick is, don't flatten. Keep reducing the spatial extent. Okay, keep reducing and reduce until you reach 1x1. Eventually you will reach there, right? If you keep doing convolution and max pooling. At the end, you're going to be there, like it will be just 1x1. Now, once you have 1x1, then again, you don't have to have like fully connected layer at the end. For 1x1 feature map, what you can do is you can actually use a convolution whose shape is 1x1. Okay, so it will be just one value. And of course, like it will have some depth depending upon how many channels you have. And so again, you can perform that convolution operation on that 1x1 activation map. If you think about that in more depth, that's exactly what you do in your fully connected networks as well. Okay, so the operation is actually not different. But still conceptually, you can define this as like a convolution network. Okay, so it is fully connected layer because, let me actually quickly describe. I think it will be useful. So let's say you start with some resolution 28x28, and let's say 3 channels. And at the end, you have a lot of convolutions, a lot of max pooling layers. You reach to 1x1 and some number of channels. We don't care like how many channels you have. Then what will happen if you try to flatten this? So this is one way. Then you will get C features out of this, right? That's what like flattening does. It just take like all the activation values and create like a linear vector. The second way could be you don't flatten and you still have like 1x1x C. Now you have C values, and let's say you want to add a fully connected layer to make 1,000 predictions. So you will have 1,000 different neurons, and you will have 1,000 times C weights here, right? In this case, what you do, you have a 1x1 kernel, and you know that depth of that kernel should be C, right? Because you're applying kernel, because you know that it should match like the depth of your activation map. And to make 1,000 predictions, you need 1,000 different kernels, right? So this will just give you one value. So you need 1,000 such kernels. And at the end, if you think about, this is exactly like your fully connected layer, because in convolution, what you do is you just take linear combination across your depth. That's how your convolution kernel works, right? And the same operation is actually performed when you have a fully connected layer, where for every neuron, you compute linear combination of all the neurons in the input layer. And you do that 1,000 times for 1,000 different neurons. So basically, the mathematical operation which is happening is exactly the same, but it's just like a different way of representation. Okay, so I will tell you like why this is very, very useful and what is the actual use case here. Of course, you can use this for classification as well, but there are like more interesting aspects where this plays a very, very important role.